In this video, I want to talk a little bit more about the relationship between our free energy change, delta G, and our standard free energy change, delta G naught. So our free energy change, delta G, this we use to predict spontaneity. So is our reaction going to be spontaneous or non-spontaneous? Do you remember that a spontaneous reaction always brings us towards equilibrium? So predict spontaneity, if we were to look at our equation for it, it does relate to our reaction quotient Q. So we're not at equilibrium yet, right? We're trying to predict which way it needs to go, right? Is it going to go spontaneously or non-spontaneously to get to equilibrium? Delta G naught, this predicts whether it's reactant or product favored at equilibrium. So remember, if we're at equilibrium, our free energy change, delta G, is equal to 0. So we're not worried about spontaneous or non-spontaneous because we're at equilibrium, right? A spontaneous reaction takes us towards equilibrium. Here we are at equilibrium, right? This relates to K. Our equilibrium concentrations or partial pressures are equilibrium concentrations or pressures. So relates to K. What we're trying to determine here is at equilibrium, is it reactant or product favored? So mostly reactant or mostly products. Again, remember K, if we think back to our equilibrium constants, that is going to be our concentration or partial pressures of products over reactants. So if it's greater than 1, right, I'm going to be product favored. If it's less than 1, I am going to be reactant favored. And we're going to do this graphically. I did start to sketch a graph here. So let's pull it up a little bit, just so we have some more room. So I do want you to write this down. So if you need to hit pause to get caught up, I'm going to have on my x-axis here, we have our free energy, so G. It's not delta G, not free energy change, just G. And then on my x-axis, I have my reaction. So over here, I have my reactants. And then this dotted line, I just kind of put there as an endpoint just because it's easier for me to actually draw the curve if I have products. So this dotted line here is just representing my products. So as I go in this direction, I'm going from reactants to products. And then this curve tells me how my energy, right, my free energy changes as the reaction progresses. I'm starting out here, I'm ending here, we are hitting a low point here. So please, again, get this sketch down because I'm going to write all over it and I want you to have it in your notes. Do be careful when you draw this that you try to get your curve to look like mine. It's kind of one of the important things is that the low point, kind of like my low point is right here, it's not centered, right? It's right of center, which is going to be important. So you want to try to replicate that. Okay, so hopefully you have it written down. So this point here, this is going to be my energy of my reactants, right? This here is going to be my free energy of my products. And because I have more room over on the right, I'm going to just draw these over here. So this is, I guess I don't really want to point there. So my free energy of, and it is at standard for my reactants. And then this point here is my free energy at standard state of my products. And then remember how we're calculating that change, right? Delta G. Is going to be my free energy for my products minus, let's move it over because I'm not going to have enough room, minus my free energy for my reactants. right? Remember, our change is always final minus initial. So my final is my products, initial is my reactants. So if we go back up and look at this one that we just did, the difference between here and here is going to be my free energy change at standard state. And in this case, because my products have less energy, right, I'm writing them down lower than my reactants, I'm subtracting a bigger number from a smaller number. So in this case, my free energy change is going to be a negative value. So it's going to be less than 0, right? It's going to be negative. And what that tells me, if we go back and look at this equation, times the natural log of K, right? I know that this is a negative value, right? My products have less energy than my reactants, so when I subtract it, I get a negative value. I do have a negative sign in my formula, so what that means is that this needs to be positive, right? K needs to be a positive value. Remember again that K, if we go back up, is products over reactants. So in order to have a positive value for the natural log of K, I need to have K greater than 1, right? If that value is going to be positive, the natural log of something that's a decimal, something that's less than 1, is going to be a negative value. So I am product favored, right? K is going to be greater than 1, and this is product favored. We can add that up here too. So if you have a negative standard free energy change, that does mean that is going to be a product favored reaction. To find where my equilibrium is, where I'm at equilibrium on this graph, it's going to be the low point. So if we look, I'm kind of dropping down and then it starts to go back up. That low point is going to be where we're at equilibrium, which isn't always the easiest to find. If you think about maybe like taking like a marble or a ball and dropping it kind of at the top, it's going to roll down, and like where it settles in is going to be the bottom. So it's about right here, I would say, is our low point. So this is where we're going to be at equilibrium. And remember how I said that we want to make sure that that low point is right of center, right? We want it closer to products. The reason we wanted that is because we are product favored at equilibrium. Right? Our value for our equilibrium constant is going to be greater than 1. Right? And we're reasoning that through using this equation. How we're going to determine our free energy change, delta G, is we're going to take the slope of our tangent lines. So we're calculating delta G not by doing, right, products minus reactants, or the energy of products minus reactants. To calculate delta G, it's the slope of the tangent line at any point on our curve. And I'm really horrible at drawing tangent lines, so kind of bear with me here. But if I was to draw tangent lines, right, if I was to draw one here, right, it's going to look something like this. That's going to be a negative slope. If I was to draw one sort of here somewhere, it's going to look like this, also a negative slope. If I go to the other side of my low point and draw tangent lines, they're actually going to have a positive slope. So kind of what that means for us, right? If it has a negative slope, that means that my values are actually going to be negative. So anything over here, delta G, or the slope of my tangent line, are going to be negative values. So let's actually write it that way, negative values for the slope of the tangent line. I'm just not going to have room to write all of that. So negative delta G. So what that means is that it's spontaneous until we get to that equilibrium. Remember, spontaneous reaction is always taking us towards equilibrium. And then over here, once we're past equilibrium, our slopes became positive, right? And remember, positive slopes, that's going to give me a positive free energy change. And that's going to be non-spontaneous. It takes us away from equilibrium. So I don't have quite room to write all that. So I'm just going to write positive delta G, right? Because it has a positive slope. You might want to add that if you can fit that in there somewhere. That means it's going to be non-spontaneous, right? These take us away over here, right? These guys take us towards So remember, a spontaneous reaction always takes us towards equilibrium, right? Again, if I was to make a tangent line any point on the curve here, before I get to that low point, it's going to have a negative slope, negative values for delta G, spontaneous. After our equilibrium point here, a slope to any point on the tangent line here is going to have a positive slope. That's going to give me a positive free energy change. It means it's going to be non-spontaneous. It takes us away from equilibrium. So let's look at another one. So I have another one drawn for us here. I don't have the dotted line in, but same sort of idea, right? This is going to be where my products are. So reactants over here, products over here. And if you guys want to sketch this one, that would be a great idea. And I will let you do that. So hopefully you did that. So reactants, right, products. So this is my free energy for my products. Drawing this one over just because I want to write them on the same side. This is going to be my free energy for my reactants. And then again, the difference between these two is going to be my free energy change. It's always going to be products minus reactants, this time because my products have more energy, right? They're higher up on the graph than my reactants. We're actually going to end up with a positive value. So delta G is going to be greater than 0. It's going to be a positive value. And what that means for us is this is going to be reactant favored at equilibrium. My value for my equilibrium constant is actually going to be less than 1, right? If we were to look at our equation again, delta G naught is equal to negative NR times the natural log of K, right? This time I have a positive value here because of this negative sign. That means that this has to be a negative value. So that means that K is actually going to be less than 1. A number less than the natural log, or the log of a number less than 1, is going to give me a negative value. So reactant favored at equilibrium. Looking at our graph here, again, our equilibrium is going to be the low point, which is, I don't know, somewhere around here. I didn't draw that very well, but here we're at equilibrium. Again, that line is closer to reactants than it is products, right? Reactant favored. my equilibrium constant is less than 1. Right? Again, remember our equilibrium constant is products over reactants. I have more reactants, my number on the bottom is bigger, so my equilibrium constant is less than 1. And then again, our free energy change, delta G, is going to be slopes to the tangent line. So anything over here is going to have a negative slope. It's going to be spontaneous. It's bringing us towards equilibrium. Anything over here are going to have positive slopes. They're going to have positive values for my free energy change. They're going to be non-spontaneous. They're taking us away from equilibrium. Sorry, just scrolling up here. Let's write positive slopes. I have a little bit more room. So positive delta G, non-spontaneous. And then kind of like on this one, this is what I was scrolling up for, right? I couldn't quite fit all of this. This time I can't quite fit all of this, but it's the same sort of idea. So negative slopes, negative delta G. We're just going to write part of it again, which means it's spontaneous. And I'm not talking about just all that area under the curve. I'm talking about the slopes of the tangent line on the curve, right? If I'm talking about that slope or that slope, they're all negative values. Positive slopes, and so on.